Welcome everyone to this third NEPSI Tech Talk. Just a couple things to talk about while we're opening here. First, the presentation today may run a little bit over 30 minutes. I apologize for that. Also, PDH. We are offering PDH certificates after this presentation. Please check in at the beginning and also check in at the end with the code, and we will be able to get you a PDH certificate either by email or through the calendar invite that we have. These presentations are recorded, so if you miss the presentation or if you can't watch it to the end, you can always get the recording on our YouTube channel. So please go to our YouTube channel, maybe give us a thumbs up also, and get more people to attend these Tech Talk sessions. They are a bit of work. If you got questions, feel free to ask those in the chat box on the YouTube channel. I may pick those up during the presentation, but if not, definitely at the end I will pick up all questions and answer those questions at the end. NEPSI is looking to improve on these presentations. We are taking ideas from the people that are watching it, and we're also coming up with our own ideas. In the coming weeks, we will be having interviews with some of our vendors. They're subject matter experts. The first one that we'll be looking to do will be with ABB and their transient-free switching technologies. We will be talking about their DS1 switching technology, their diode pre-insertion technology, and also their new VD4 transient-free switching technology. So look out for that. That will definitely be an interesting subject matter. And if you have any other subjects or vendors that you would like us to talk with, please reach out to us and we will have them on also. So today we're going to be talking about power factor, and I'm going to kind of start this presentation today with something that's kind of fun. We all see this analogy, and I have myself here a Guinness. We all see this analogy with a beer to explain power factor. So we will go through this analogy. I'm going to try to add to it a little bit rather than just have the figure. So as I pour this glass, let me just raise this up here, you see there's foam on top, and a Guinness, in a sense, because it's a nitro beer, you could say has a very poor power factor. The foam on top is related to what we would call reactive power, and the beer in the bottom being active power. So in a sense, the beer is the part that quenches your thirst, and the foam is a necessary byproduct, and I guess Guinness believes in a poor power factor. What's interesting to note here is that if the foam is 50%, if the beer glass represents kVA, the full glass, right, and we were to divide the kW divided by the kVA, in other words, the volume of the full glass in the denominator and the foam on top, we would have the power factor. And my question to you is, would you be able to calculate the power factor angle? And you could pick up your calculator, some of you, if you remember your high school trigonometry. And incidentally, knowing trigonometry is a requirement for understanding power factor. It really is a trigonometry type problem. You would type in, if it were 50%, you would type in 0.5, and you'd hit arc cosine, and it would give you an angle of 60. So in this beer here, power factor has improved quite a bit. When you add capacitors, and I'll put my finger here, add capacitors to a system, you in a sense correct power factor. We know that oftentimes when you stick your finger in, especially in beer or in soda, the foam will drop away. So think about adding capacitors to correct power factor, and that's what we're doing here. The other thing is, if you pour a beer poorly, you have poor power factor, more foam. Something else to think about. It's a bit of a pretty good way of thinking about it. A poor pour results in a poor power factor. So let's get on to the presentation today. I'm going to flip over to the screen. And so again, today's discussion is about power factor, and we'll move on with the presentation. Reminder, PDH, make sure you send a message to the chat box to make sure that you check in, and we'll check for the code at the end of the session. So today we're going to talk about power factor common analogies. We've already discussed one of those today. We're going to talk about power triangle, the power factor terminology. We're going to review the single-phase and three-phase power equations. In a sense, it's easiest to talk about power factor with equations. When you come right down to it, this is a mathematics problem, and we're going to go through those equations. We're going to discuss why you should care about power factor. What's the importance of power factor? And really, when you think about power factor, is the number one piece of knowledge you should have if you're involved with power factor, if you're involved with power system analysis. The number one important aspect of power system design. So power factor is the most fundamental thing you should know. And this is true whether you work in a plant environment as a maintenance person, or if you're responsible for the facilities, or if you're working at an EPC and designing systems, you really need to understand power factor. So first, let's come up with a mathematical definition. Power factor is just a ratio of power, power kW divided by apparent power kVA. Okay, and it's equal to the cosine of theta. And here's the trigonometry coming into play. So power factor kW divided by apparent power divided by apparent power kVA is equal to cosine of theta. That theta, incidentally, here is equal to the same theta that exists between the voltage and current waveform. So if you had a circuit and you're supplying current into the circuit, as we show over here, if there's some inductance or some capacitance, the current waveform will either lead or lag the voltage waveform by an angle theta. That value of theta here is the same value of theta here, same exact value. So those ratios represent a phase shift in the voltage and current that you have during current conduction in the circuit, whether it's capacitive or inductive. In a purely resistive circuit where there is no X of L, no X of C, no capacitive reactance, no inductive reactance, the phase angle would be 0 and the voltage and current would be on top of each other. Another thing that's interesting to note is if you come up with an impedance angle, in other words, we calculate the impedance over here, and in that case it would be the square root of X of L squared plus R squared, right? It would be the summation there, square those two terms and take the square root of it. That would be the impedance, and it would have an associated angle associated with it. And that angle is the same angle as we note here and here. So all the same angles, and that's something that you should take note of, understanding what those angles are. We've already gone through the analogy with the beer. It's a good one. I think it lacks some technical features, and I like other ways of explaining power factor, other analogies. One is an airplane. If you think about an airplane that's flying in a crosswind, there is a direction, there is a motion in the direction of your desired direction, and there's also a motion according to the crosswind. The plane has to fight the crosswind, and therefore there are two components, one that's horizontal, one that is in a direction of flight, and your resultant velocity would change based upon that. So that's one way to think about it. Sailboats have the same type of issue when it comes to crosswinds, and if you think about sailing a boat within a river that has current flow, you would have a similar type of analogy. Another one I also like is here is you got a horse pulling a rail car along along a track. The horse can't walk on the tracks; he needs to walk off the tracks, and therefore the rope is tied to him through this angle. The desire is to pull the car along the tracks in this direction. That represents the forward motion. But there is also a perpendicular component. And this one really shows very well what power factor is. Reactive power, in this sense, is a perpendicular component, one that is 90 degrees out of phase with kW. So remember, reactive power is usually associated with a quadrature component, one that is 90 degrees phase shifted from the real power. So I like this way of explaining power factor. It's a very interesting way of explaining power factor. We start off with the very simplistic system where we have the instantaneous power equals the instantaneous voltage times the instantaneous current, those two values. In a purely resistive circuit here, kind of show it here in a purely resistive circuit, we have voltage and current in phase with each other. So we have the orange waveform, which is current. We have the blue waveform, which is voltage. We multiply those two times each other according to this equation, which is for instantaneous power. And we get what we would call the instantaneous curve here. This instantaneous power curve is grade curve. So -1 times -1 is what? It's +1. It puts you up here. You can see here the voltage and current are in phase. It's 0 times 0 is 0. We got 0. So we developed this grade curve, which is the instantaneous power flow to the load. And you can see that if you were to take this into Excel and you were to average all these values, we would get this value of 0.5. 0.5 would be the average power flow to the load. And this is how power systems work. We have this instantaneous power flow, but then we have an average power flow. We oftentimes reference this as RMS power flow. So if I were to go to an inductive circuit, and in this case, I do the same analysis. I multiply the current times the voltage everywhere along the waveform. You will see that I get a grade curve now that's straddling the 0 axis here. Okay, so at this point here we have a -0.5, and that's because we're taking a negative, maybe this is 0.707 times a plus 0.707. We're ending up with a value of down here of -0.5. And we do this along the whole ways. If we were to then take the average of this curve, the average power delivered to the load is 0. No power is being delivered to the load. And this is kind of interesting. This is what happens in an inductive circuit. A purely inductive circuit is that power goes to the inductance of the circuit. It builds up that magnetic field, and then the magnetic field collapses and sends the power back to the source. So therefore, no net transfer of real power to the load. We can do the same sort of thing with a capacitor. In a capacitor, the current will lead the voltage by 90 degrees, and that's what we have shown here. And we can multiply the volts times the amps, and we get a grade curve that straddles the 0 axis. And again, no net power is sent to the load. And so in this case, what's going on is the current is flowing to the capacitor to charge the capacitor, to put charge onto it, and then it is sent back the following half cycle. And this is the way a capacitor works. So no net power transfer to the load. So this is really the bare essence of power factor. In reality, many circuits will consist of some resistance and some capacitance. And if I were to flick through here, I've added a little bit of resistance to my capacitor, and you can see, you can watch the grade curve, and I can get a various values of real power flow and reactive power flow to the load. And we can continue in the inductive side. So we have an inductive circuit here where the current lags the voltage, and then we have a capacitive circuit here where the current leads the voltage, and it becomes inductive. And basically the best we can do is a transfer of power of 0.5. Transfer of power of 0.5. So on to the next slide. Let's go on to the next slide. So we oftentimes use a power triangle. We would very seldom get into the waveforms. When we do power system analysis, we don't talk about these waveforms. We don't get into instantaneous power. When we're designing power systems, we will more or less resort to equations and to the power triangle. So let's talk about the power triangle here. Power triangle is shown down here in the lower left. We have on the x-axis, we always draw power, whether it's the negative x-axis where we're generating power, or it's the positive x-axis where we would be consuming power. Okay, so we're looking at this from a load standpoint. And the y-axis we always draw up, either as a plus Q for an inductive circuit or negative Q for a capacitive circuit. And the angle theta here is the power factor angle. Okay, so we have what's called the apparent power is the hypotenuse. So just from your days in high school, you know you can take the power squared, add it to the reactive power squared, and take the square root of that and come up with a hypothesis here, and that would be called the apparent power. We could do that also for a capacitive load. Oftentimes we are talking about power factor, we're talking about reactive power, and we have this term plus J minus J. This is a complex number, and we represent apparent power as a complex number. It will be P plus or minus JQ, right? So P plus or minus JQ. P can be plus or minus. Typically we would say plus is a resistive load and it's a load. If P, when we're looking at from a load standpoint, were negative, it would be a generator. So proceeding on, without a doubt, the most important thing to know about power factor is trigonometry. And you remember from our high school years, we have SOHCAHTOA. Okay, we have S equals S, which is the value of S here. In this case, it would be complex power equals opposite over hypotenuse. Okay, so we use this sine function if we need to figure out what Q is. So the complex power is equal to opposite, which is Q, over the hypotenuse, which is S, Q over S, and that's what we come up with here. So if we know two of the three values, we can calculate everything else, and that's really the key here, is understanding that you can use trigonometry. It's your fastest way, without a doubt, to the answer is to use trigonometry. Putting SOHCAHTOA back to your memory and using SOHCAHTOA as a way to calculate P, Q, and S and theta is by far the easiest thing to do. So there's some terminology to think about. You have power factor is a number that's expressed between 0 and 1. Okay, so a zero power factor would be either a purely inductive or a purely capacitive circuit. A power factor 1 would be a purely resistive circuit, one that just consumes real power, kW or megawatts. Sometimes it's discussed as a value in percent. Okay, so remember you have kW divided by kVA, kVA being the total, being the full glass of beer, and kW being the liquid portion of it, right? And that's described as a percentage value. So oftentimes you'll hear somebody say, I have a 0.8 power factor. If they have to tell you, is it lead or lag? 0.8 lead or 0.8 lag? And this is really describing whether the system is capacitive or inductive. A lagging circuit will be inductive. A capacitive circuit, okay, will be leading. Okay, and this is really the important thing. Lead, lag, capacitive, inductive. We need to know when we talk about power factor, is it inductive, is it capacitive, or is it leading, or is it lagging? You have to differentiate between the two. Very important. Most industrial systems without power factor correction will be lagging just by their nature. Most loads are lagging just by their nature. Incidentally, reactive power is the power component that builds the magnetic field around conductors. It's the magnetic field that's inside transformers. It's the magnetic field that's inside motors. Without the reactive power that flows into these devices, these devices would not work. So reactive power is necessary to create that flux that enables motors and generators and transformers to operate. If we have unity power factor, what it means is the power factor is equal to 1.0. It means the angle theta is equal to 0, and we have no Q, no reactive power flow. It's that simple. We would describe them as either kW or megawatts. When you think of a circuit that's purely resistive, think about a light bulb. It generates heat, it generates light. There is no reactive power associated with a light bulb. We have lagging power, and this would be an inductive circuit or an inductor. And in this case, we draw Q up on the axis. Say if we're in the PQ plane here, we're plus J minus J. We draw Q perpendicular upward to represent the inductance of a network. And theta is equal to 90 degrees if it's purely inductive. And here you want to think about air core reactors, and here we have what's called a shunt reactor. And remember, when you think about shunt reactors, what you can think about is that shunt reactors consume VARs, Think about VARs as a power system parameter, and shunt reactors consume VARs. It's a VAR consuming device. It's the best way to think about a shunt reactor, and this is how we would draw it in terms of on a PQ diagram. You also have a capacitor, which is also a purely capacitive device. We show it here, and in this case we're drawing Q downward. It's got the units of kVAR or megavars, and we're drawing it down. Again, here, think about a capacitor bank. In particular, think about NEPSI's capacitor banks, especially at medium voltage. They supply VARs. So think of capacitor banks as a supply of VARs. So shunt reactors consume VARs. Capacitor banks produce VARs. Easiest way to think about it in terms of your power system parameters. So a typical lagging power factor of an industrial plant, and we have some P, some Q, and we have the complex power S. So if you were to go into an industrial plant without reactive power, you would expect to see a power triangle that looks something like this. We would have a positive angle of theta, we would have a value of positive Q, and we have some amount of power consumption, a load. And that's what this looks like here. We have some megawatts, some megavars, and here's that plus J. That's a complex number. Megawatts plus a J megavar, right? It's a complex number. And think about a motor. Typically motors have a power factor of say 0.85 to 0.92 under full load conditions, and you would have a power factor angle. If I had a value of say 0.9, I can go to my calculator, 0.9, and hit F, a cosine, arc cosine, or inverse cosine, and it would be a 25 degree angle here. Okay, so a power factor 0.9 gives you a 25 degree angle. Another thing that's interesting to note is if the power factor is about 0.72, both the VAR consumption and the P and the Q are equal to each other. At about a power factor of 0.72, kW and kVAR, the reactive power and the real power of the network are about the same. So it's a good point of reference to realize that a power factor around that 0.72 mark represents a system that is drawing equal amounts of power and equal amounts of reactive power. In terms of power equations, and this is what we really work with, we have three-phase formulas and single-phase formulas. And I can tell you from my world, I'm almost always working in three-phase formulas. It's almost primarily my 100% concern. The real power, P, three-phase, is equal to the square root of 3 times the voltage line to line times I times the cosine of theta, cosine theta being the power factor angle. It's important to realize that you want to never forget the square root of 3. Never forget the square root of 3, and always use line-to-line voltage when using these equations. Single phase, and in the single phase formula case, we're dealing with line-to-neutral voltage all the time. Line-to-neutral voltage. I had a professor, I'll tell you a story, I had a professor once upon a time that if you forgot to use the square root of 3, he would divide your test score by the square root of 3. So if anybody had that professor, let me know, but that is absolutely crazy. And there were some people who did forget to divide or multiply by the square root of 3, and that was an automatic 57% of your grade, 1 over square root of 3, 0.57. You would remember that if you got hit with that test score automatically. So why should you care about power factor? The first thing is potential savings. In an industrial environment, especially in North America and in many parts of South America, the electric utility will charge you for a poor power factor. The poor power factor will show up on the electric utility bill in two ways. One, what is called kVA billing. They're charging you for kVA. In other words, the complex power that your system is drawing from the system is called a kVA demand charge. Some utilities on their rate structure, on their tariff structure, will have this on their bill, the kVA demand charge. Look for what that is on the utility bill. That's the first thing you look for. If you find that you have a kVA billing, you can look to determine what your cost savings are, because when you correct a unity power factor, what you have done is you've minimized the value of kVA. You brought kVA to a minimum value. All that is left is the real power, and that real power is what you need to run your plant. So putting power factor correction in there, in a sense, is reducing kVA to the minimum value, and what's left is kW, and you can reduce that kVA demand charge. There are also other utilities that will charge based upon power factor. They measure the power factor over a period of time, over the 1 month period of your bill, and they determine what your average power factor is. Or they say, well, what is the power factor at peak load, at peak demand, at peak kW? It changes from one utility to the next. And then they will make some kind of division. They will potentially divide your demand charge, your kW demand charge, by the power factor. So obviously if you have a 0.7 power factor, they would take your kVA demand charge, divide by 0.7. If you improved your power factor to 0.95, it would be your kW demand charge divided by 0.95. So you have to go to the tariff structure and look for the potential savings. But in North America, there are sometimes electric utilities that will have a payback period that is less than 1 year. And then a lot of capacitor banks are purchased on the basis of payback, and they're looking for paybacks of 1 or 2 years. Another thing to think about is improved voltage regulation. When you add capacitor banks to a load, if we have a load over here, what we in a sense are doing is we're reducing the power flow through the network. We're reducing power flow through the network. We're reducing the current flow through the network. And you know V equals I times R, or V equals I times X, right? If you think about current flow here, if we can reduce the current flow, we reduce the voltage drop across the line. And so what we're doing is we're improving voltage regulation. So oftentimes power factor correction is important to improve voltage regulation. If you're in facilities that are using very poor power factor devices, induction furnaces and things like that, having a significant amount of reactive power flow through that network causes a significant voltage drop, and that's a power quality concern. And then increased system capacity. We've already stated with the potential savings here that if you add capacitor banks to a system, you reduce the kVA. When you purchase a transformer, you purchase a transformer based on kVA. If we can reduce the kVA by adding capacitors to the network, we may be able to put a smaller transformer in. Or if we have a load, okay, a system, a factory, for instance, that's expanding, and they've reached the capacity of their transformer, one thing they can do to defray the cost or to postpone the cost of a new transformer is they go out and they purchase capacitor banks, reduce the kVA draw from their plant, and they may get a couple extra years out of their system before having to purchase a transformer. Independent power producers are also involved with buying capacitor banks and harmonic filter banks. Oftentimes it's not because they're looking to correct power factor, it's because they did an interconnect study. And the interconnect study had determined that power factor correction or reactive compensation, really reactive compensation, was necessary. That might be because of voltage collapse or some other type of dynamic instability issue associated with that wind farm. But this is an interconnect issue, is part of the interconnect agreement between the renewable developer and the utility that they're connecting to. And it would be to meet their interconnect requirement. So oftentimes it's not power factor correction for the purpose of trying to save on some type of cost. It's because it's a requirement to meet some other requirement that has been put forth in their interconnect agreement. Electric utilities have an interest also in power factor correction, and at the distribution level, loss reduction is by far one of the primary reasons for adding capacitors. They put pole mount capacitor banks in to reduce the power flow across the network. Again, if you think about it, if you reduce the kVA through the network, in other words, you reduce the current flow through the network, you reduce the I squared R, you reduce I, right? And therefore you reduce the I squared R losses across the network. And that is a primary reason for adding capacitor banks to these networks. They also have an interest in voltage regulation. Distribution systems oftentimes have very long lines, and they might be anywhere between 2.4 kV to 13.8. But do realize that 13.8 kV probably represents a good 80% of North Americans' primary distribution voltage levels. Voltage drop becomes an issue if it's 20 or 30 or 40 miles long. Voltage regulation is an issue. If we can reduce the voltage drop because we reduce the reactive power flow through the network, we can justify the cost of capacitors and installing those. And then again, system capacity. We've talked about this already. The utility might be pushing up against their transformer rating at their main substation, and one way to reduce the kVA draw through that substation is by adding capacitors. Power factor correction. So we talked about what power factor is at this point. I think we have a good understanding of what power factor is. Now we have power factor correction. And really, power factor correction is about adding VARs to the network to correct the power factor. So remember, we were talking about VARs, the load, the factory, the motors in the factory. They are devices that consume reactive power, the VARs. Okay. When you do power factor correction, what you're doing is you're adding VARs to the network. If the VARs are being added to the network locally at the factory, then the utility does not need to supply those. Remember, the load will dictate the amount of VARs that are needed. A motor is going to take in a certain amount of VARs for it to operate. Whether you put power capacitor banks there or not, the load at the motor will consume the same amount of VARs. The question becomes, where do those VARs come from? They can come from a local source, those local sources being capacitor banks. It could be static bar compensators, which is a electronic form of a capacitor bank. Okay, so it's a basically electronic capacitor bank. Actually, I'm wrong here. I'm sorry. I'm speaking out. A static bar compensator, okay, which is a fast switching capacitor bank using thyristors. And then we have StatComs. Okay, so StatCom is the electronic version of a capacitor bank. We have synchronous motors and synchronous generators. Remember that synchronous motors, synchronous generators, and synchronous condensers are all devices where they have a field winding. Those field windings can be overexcited to produce reactive power, to produce VARs. So some paper mills use large synchronous generators, for instance, and large synchronous motors. They will be supplying their VARs locally at that main bus. So NEPSI is a supplier of metal closed reactive compensation solutions, metal closed cat banks, metal closed harmonic filter banks. All of these industries, whether it's mining, solar, wind, and oil and gas, use our products. Our products come in both large and small sizes. It really depends on the industry we're serving into and what their power demand is. From an industrial standpoint, in almost all cases, potential savings is the primary reason for power factor correction. The industrial plants are not looking to reduce their losses. Their primary concern is utility payback. So the first thing to think about is if you're working at a facility and you want to know, well, should I do power factor correction? Well, go grab the utility bill. Look at the utility bill and determine, do you have a power factor penalty? Do you have a kVA billing? If you do, what do you think your payback is? The payback can be very, very short, or it can be many years. You have to determine what the return on investment is. So usually the approach is to go to the utility bill, check out your utility bill, determine what your possible savings are, go to a capacitor supplier and get a proposal, at least a budgetary price, determine what that cost is and compare it and see if the return on investment makes sense or not. System capacity, we've talked about this already. You can avoid the cost of buying a new transformer. There is a very simple formula for calculating the released kVA for power factor correction is here. Basically, it's 1 minus the ratio of power, your initial power factor divided by your corrected power factor times your initial kVA. A very simple formula. I gave an example over here. If a plant, correcting a plant with a 0.8 lagging power factor to unity would release 20% of the plant's kVA. So that's pretty significant if you think about it. Add a capacitor bank and avoid the cost of a new transformer. It could be a significant cost savings. We can bump back here. We also have improved voltage regulation. So improved voltage regulation, again, if you're a system with a very poor power factor, you are going to be drawing reactive power through the impedance of the network. Okay, and this is an approximation of voltage drop. It comes from the IEEE Red Book. Basically, voltage drop across an impedance of the network is equal to IR times the cosine theta. Cosine theta being the power factor angle plus IX times sine theta. If you think about what's at the service entrance of an industrial facility, it's the transformer. The transformer impedance is typically about 10%. The X over R ratio of that transformer is usually on the order of 20 to say 25 or 30. So the resistance is very low. So your voltage drop according to resistance is not that bad, but the voltage drop according to the reactance can be significant. And with a very poor power factor, sine theta can start to approach 1, and that therefore means that you have a pretty significant voltage drop. So improving power factor eliminates this voltage drop component, and that's really what you're looking to do. From the electric utility standpoint, voltage regulation is a possibility. Remember, voltage regulation can also be controlled by voltage regulators. So utilities have multiple options for regulating voltage, for controlling voltage drop across their distribution line. But capacitor banks represent one of those. But really, the real reason is I squared R losses, the amount of losses across the transmission or distribution system. What is the percent loss reduction that they can get? When you have many, many miles of distribution lines, the loss reduction can become significant. This is not true for industrial plants. I often get phone calls from industrial plants where the customer is saying, "Hey, I want to determine what my loss reduction is. I don't have power factor penalties, but I want to buy capacitor banks and I want to justify them on the basis of loss reduction." I can tell you, in 25 years of doing this, we have never ever sold a capacitor bank to an industrial plant on the basis of loss reduction. It just will not pan out. We typically do not entertain such calls nowadays. But from a utility standpoint, the loss reduction can be significant. And I do a quick analysis here, and I say that if we have a system that's operating at 0.75 power factor, and I were to go to 1.0 power factor, I would get a loss reduction of 43%. And that's a pretty significant loss reduction if you think about a utility on a utility-wide basis, all of their distribution network, to reduce the losses associated with on their network by 43%. So power factor correction on the power triangle, and that's what I show here. And the first thing I think we should note is you can use the power triangle to calculate power factor correction, to determine the amount of capacitors necessary, I note it here, to correct power factor. By far the easiest method to calculate VAR requirements in the system is by using this top equation here. And you can do this with a calculator. Okay, so just use your calculator. All you have to know is what is the power factor angle. We talked about this twice already. The power factor angle, you take the inverse cosine to get the power factor angle. So we can go with knowing what the initial power factor angle is and subtract it from the final power factor angle and come up with a ratio, a multiplier, and that's what tangent theta minus tangent theta prime is. So I'll give you an example. If I'm going from 0.75 power factor, 0.75, I would hit 0.75, I would hit arc cosine and then tangent. That's it, I get a value of 0.88. I would go 0.95, or as my final power factor, I hit 0.95, arc cosine, tangent, subtract those two, and I get a value of 0.55. It's that simple. 0.55 times the power in the plant. And remember, power is not changing. The requirement for power within the network, what's making the motor, what the motor is turning, will not change with power factor. That's a constant. What changes is reactive power flow. So this is by far the easiest way on the calculator, knowing that simple formula. Another way of doing it is to use the triangle and to draw everything out, and you can do that here. The end result is you are coming up with the same equation. And so what we show over here on the right is we have an initial complex power here, and we have an initial value of Q, okay, which is QT, and we have an initial value of P. When we do reactive compensation, we add some capacitance QC. We're adding VARs to the network, a value of QC. That makes this triangle, and incidentally, this value of theta, power factor angle, decrease, and we end up with less VARs, the value of QT here. Okay, actually, value of, well, I don't quite, the diagram isn't quite right, but we end up with this right here, this value of Q. Okay, smaller value Q. There's other ways of doing it. One is this is a popular table. So if you don't like trigonometry, you can go to a table, type in power factor table, and Google images, and hundreds of them come up. You can develop the same table using that tangent theta formula from the previous page. Same thing. But incidentally, what you do is you enter. You determine the desired power factor, and you enter that on the horizontal axis here, and then you go on to your initial power factor on the vertical column here, and the result is we get a multiplier of 0.487. So we're going from 0.75 to 0.93. The multiplier is 0.487. If I did the same thing on my calculator, I could go 0.75 FA cosine tangent. 0.93 f a cosine tangent minus, I better get the same value, 0.4867. So same basic value. And this is how the tables work. Another way of doing it, no calculator, no trigonometry required. When you think about the PQ diagram, it's important to note, we talked about the negative p-axis, but negative p-axis here represents power generation. When we're generating power, we can also be either consuming reactive power or putting out reactive power. In general, generators are designed to put out reactive power. They supply reactive power to the network. So you have what they call the PQ plane here. We have minus J on the bottom axis, meaning we're in the consumption of VARs, and then plus J, we're actually have it back. We're producing VARs on the negative side here and consuming VARs on the positive side here. So, as a reminder, please remember the PDH. There's a code here, 345. Just send that to the meeting invite or to an email, my email, and we'll get you a PDH certificate. In conclusion, power factor is by far the most fundamental aspect of power system design. I hope today you picked up power factor terminology, how to do power factor calculations, how to size capacitors for a given load, and why power factor correction should always be a primary concern when designing power systems. Next week, for part 2 of this Tech Talk, we will discuss power factor, application solution steps. We'll talk about the location of the capacitors. Do you put it at low voltage? Do you put it at medium voltage? Do you put it at the transmission level? Do you put it at the motor? Do you put it at multiple places? We're going to talk about the pros and cons of those types of questions. And then we're going to talk about the primary concerns. Last week we talked about transient inrush. We'll touch upon that again next week. But we're going to touch upon other things. We're going to talk about resonance. We're going to talk about outrush currents. We're going to talk about the concern of overcompensation. We have some customers that will come to us and they will adamantly swear that they do not want to go to a leading power factor as if the earth is flat. We will also talk about voltage rise concerns, how to calculate voltage rise, and then self-excitation, not motor excitation, but self-excitation. We will talk about self-excitation. Do you have other concerns? Before next week, ask us some questions, or perhaps go to the chat box now and ask us those questions. Let us know what they are and we'll discuss them. So we're going to go over to the chat box now and see what we have. And let's see, we have a question. It says, okay, still did not receive previous presentation. Please mail me the previous presentation. Okay, thank you very much, Matt. I hope you're getting this. Just write down that presentation, that email address, and we'll get the presentation. Okay, thank you. A couple thank yous. I appreciate that. Again, previous presentation. We will get that to you. I'm sure Matt's on it. Okay, so we have a question about harmonic analysis, and really that's another presentation. That is one that will be coming. That's like a two-part presentation. I have a great presentation for harmonic analysis, and we will be discussing that. So I'm going to flip on this questions and answers screen. So we have a question that came in, and I need Tamara, if I'm pronouncing your name right, you're saying MDI meter. I'm not sure what an MDI meter is. Perhaps you can chime in real quick with the chat and let me know what an MDI meter. But it says, does MDI meter indicate the power factor for peak timing? Not sure what that means, what an MDI meter is. Does NEPSI install them at panels? And again, we sell metal closed cap banks, harmonic filter banks. Our systems have the all switching protection control built in, but I'm not sure what a MDI meter is. I will wait a minute for you to type that in, if you could. Maximum demand indicator. So we do not install those in our panels, but typically electric utilities, when they are doing their metering, their kW hour metering, their energy metering, they will have a kVA demand meter. Normally those kVA demand meters work over a 15-minute interval, recording the energy consumption during that 15-minute period, but also recording the maximum kVA during that period of time, maximum kW, and then they calculate power factor during that 15-minute period. And oftentimes during that 15-minute period is when they are calculating your penalty. What is your maximum kVA during that 15-minute period for a period of a month, and then they're recording what the power factor is during the peak of the month, and they're recording that constantly. Incidentally, some power factor penalties are ratcheted, which means that if you record peak kVA or peak I would say peak or worse power factor, that power factor will hold for a period of say 6 months or even a year. Depends on the utility. You have to go to the electric utility rate structure, determine what type of billing they have, if the system is ratcheted or not, and also how do you calculate power factor. Is it based on peak? Is it based on average? Is it based on continuous value? It changes from one utility to the next. If you're involved with power factor studies, you have to go to the rate structure. You have to ask for the rate structure. You got to get the information, and then you got to try to get meaning from it. And incidentally, when you're doing the power factor studies, you should be getting data for a period of an entire year, because some plants will peak in the summer, some plants will peak in the winter. So you have to determine when is the peak and is it ratcheted. Okay guys, so I think that's it for this week. Please join us next week. Again, we're going to be doing application, solution steps. We're going to be talking about doing some load studies, how they're conducted, talking about the spreadsheet analysis tool that we would typically use, how you might want to fill that in. And we'll be talking about the primary concerns with reactive compensation. Remember, can you go leading? Is it an issue to go overcompensate, voltage rise, harmonic resonance, transient inrush, and transient outrush? And if you've got questions or something you want us to address, we will do that in future presentations. We tend to run these for an extended period of time, and any feedback, improvements that we can make, we would appreciate that information from you guys also. Thank you for coming on today.